Let's begin this course by defining what information and cybersecurity is in the first place. So first of all, information and different data surrounds us. We usually distinguish between data and metadata. So there's the actual data, and then we could have information about the data, which is then metadata. Information itself can have many form factors. We can have information on a computer or inside or written down on a piece of paper or simply having it in our heads. When talking about information security, the digital forms, that is ones and zeros, are usually the most interesting. Information is also processed in so many different ways. We can change the shape or form of information, and we can transmit data in many ways and in many form factors. Information security by definition is the security for information and information processing. Sometimes we think of security as only security for information, but also the security for information processing is important to include in this definition. What does it mean for something to be secure or safe? Well, often security is advertised as a product. That is because in the real world there are a lot of security-related products. There are burglar alarms, locks, security services, security guards. In the real world, these concepts are very easy to understand. For instance, we know that if we have valuables at home, we get some sort of an alarm system and possibly a camera in addition to a safe or safety deposit box. Information processing, on the other hand, is mostly digital. And in this digital networked cyber world, the real world rules that we know don't apply anymore. What is worse is that the various systems that we use are very complex. There's hardly anyone who fully understands how systems operate these days. Usually discussion about information security revolves around individual products, methods, or technologies designed to keep those systems safe. For example, we use terms like antivirus, firewall, or encryption. These technologies are mostly situated in mathematics under the science of cryptography. Cryptography, like all maths, is about numbers, formulas, or logic. Cryptography itself is the art and science of encryption. Anyway, this is all based on numbers and logic, whereas security in the real world revolves around people. There are things that people know, there are relationships between people, there are relations between people, there are relationships between humans and computers. The problem with effective information security is that computers are complex and unstable, and they often have bugs. Mathematics, on the other hand, is perfect. Reality is very subjective. Math is very well defined, and computers and people are unstable. Math is logical, whereas people are unpredictable. What security means is the big picture of users, their processes, and the tools to secure both the users and their processes. Security is not about focusing on one of these elements, and you cannot leave one side of this three-sided triangle out. We say that the context matters the most in information security. That is because security problems are seldom about technical challenges. They are seldom about the mathematics of securing something or how something is technically possible. That is because the mathematical perfection that comes with cryptography is useless if, for instance, we, as the user, select a bad password. Or if we choose to use software whose developers have made mistakes. Or if we do not understand what some security tool or technology does and why it does what it does. What is most important to understand is that security is not a product. It's often advertised as one, but it isn't. Security is a process. Security is also a chain, and chains tend to have a weakest link. And this security, the process, is also as strong as its weakest link. It's flat out wrong to say that security needs are solved with any technological solution. Saying something like that means that you don't understand the problem that you're trying to solve, nor the technology that you are using to solve that problem. You might think that a system is a technological term, but it really isn't. It's in fact a very cultural term. Eastern philosophy tended to think that the world is one big functioning system. Westerners had an opposite view. They see the world as a collection of interoperating systems. The ancient Greek philosophy is somewhere in between, thinking that parts reflect the whole. For instance, in the human body, the bodily fluids somehow have an effect on your humor and that sort of thing. Anyway, out of this, the last one, the Western worldview, may be more analogous to computing. So computer systems are networked and they are interoperating. Many other systems share this kind of philosophy too. So for instance, the elevator in a building works together with the fire alarm systems. Computers communicate with each other within networks, and computer networks work in parallel with other networks, forming even bigger networks. The internet and the network of networks is probably the most complex system. There are millions of hosts online, and each of these hosts can run hundreds of applications. Some of these computer applications work together with other applications, others communicate with networks, and so on and so on. Computer systems have several interesting features which make them particularly useful for discussing about security, both in the good and in the bad. The first interesting feature is complexity. So think of machines or tools. They are very simple. Think of a hammer or a knife, for instance. Systems, in contrast, are more complex. Systems are composed of several components which have inputs and outputs and failure rates and infrastructure. And computer systems are particularly complex. The second feature is interactivity. Systems tend to have many components which work together. Smaller systems can be components of a larger system. The third interesting feature is something called emergent features. That is to say that sometimes systems do things that they were not meant to do, or rather they weren't designed to do something. An interesting story about an emergent feature relates to the telephone. So Alexander Graham Bell, the inventor of the telephone, never meant the phone to be used as a means of communication. It was supposed to be used for announcing an incoming telegram. The fourth important feature here is that systems have bugs. A bug is sort of a fault. It's an emergent feature that is undesirable. However, bugs in some sense are not faults. So if a system is faulty, it means it is broken. When a system has a bug, it means that it works in unexpected ways. All of these four features, complexity, interactivity, emergent feature, and bugs, have a big impact on security. The impact is that a complex system, like the internet, is very hard to secure. Systems in general are hard to secure, and securing systems is a laborious and hard effort. Because securing systems is hard, there is a simple life hack or coping mechanism that is often applied. we leave the big system, the big picture alone, and concentrate on securing smaller subsystems. That's why we have many different forms of technology related to computer security, like cryptography, firewalls, public key infrastructure, and so on. We talk about these many subsystems and individual technologies because it's easier to talk about technology separately. It's easier to handle one small system than it is to handle a big one. As one might guess, leaving the big picture alone often leads to unwanted repercussions. For instance, security attacks or information leaks. Security problems can often be categorized according to the 4 features that we listed in the previous slide. For example, the somewhat recent Heartbleed vulnerability in servers. This would be a bug or an emergent feature that is an programming error caused new unwanted properties in some of the core libraries used by many web servers. Denial of service attacks are based on the premise that systems need to communicate. Therefore, a denial of service attack is based on the need for systems to interact with each other. Anyway, the point of this all is that we really must think of computer systems, all the hardware, all the software, all the networks, as parts of large, very complex, complicated systems. Let's briefly consider how to design secure systems, or the theory and practice of securing systems. So there exists both theoretical and practical information security. Theoretical security contains all of the extensive knowledge and research on security, for example, cryptography, firewalls, intrusion detection systems, biometric authentication, and whatever you can name. A practical system may use theoretical knowledge, but in practice it can be useless in the worst case. You may have heard of this quote: "In theory, there is no difference between theory and practice, but in practice there is." The point of this being, we can design ideal, completely secure systems in theory. Practical security is about compromises in the various design choices, variables, and imperfect solutions. Perfect security in the real world doesn't really exist. Finally, let's discuss about a protocol on how to secure any system, be it computer system or some other system. So in order to secure a system, let's keep in mind the 3 main principles of securing something. That is to prevent attacks, to detect attacks, and reacting to attacks. Good security takes into account all 3. So for example, consider a vault where valuables are kept, burglar alarms that notify the owners or security people of an attack, and guards or the police that react to the alarm. What often goes wrong when it comes to computer security is that we only concentrate on preventing attacks. This is because many of the tools that we use, they are based on cryptography, or such as firewalls, etc. These are the tools that are for preventing attacks, but it's less common to have tools in place to react to attacks, and often an attack is based on going around this prevention mechanism, and very often these attacks are unfortunately successful.